my screen. I'm just going to share the screen with you because if you would allow me, I just want to share a bit about Cement and Concrete SA with you. Those who've attended our previous two CONCRETEfixes would have seen some of this, but as I say, bear with me. I'm excited about Cement and Concrete SA, and I want to share this. There you go. Cement and Concrete SA was launched at the beginning of March, and since then we have, let me just get there again, bear with me. I trust that you can all see my screen. My technology skills are leaving me today, but we welcome today Professor Hans Boyshausen, who's going to talk to us about the design for concrete durability, international trends and South African perspective. If you're not a member of Cement and Concrete SA already, we really want to urge you to become part of this member, to become part of this body, to be part of the future of Cement and Concrete in South Africa. And just a few screens, our partner members are AfriSam, Lafarge, PPC, and Sepaco. Our gold member, CRISO ABE Group. As silver members, we've currently got Costra and Sika. And we welcome our bronze members, and these were correct as paid up members as of yesterday. ASHAC, BAMR, JG Africa, LNS Consulting, Meltval, Metier, UPAT, VSL, and as an associate member, Concrete Manufacturers Association. We also welcome these academic members who've taken up the offer of free academic membership for their organizations. Welcome to University of Stellenbosch, University of Cape Town, University of Pretoria, University of Johannesburg, and University of the Witwatersrand. Briefly, membership benefits include access online to the Information Center, access to the advisory desk, discount on School of Concrete Technology courses, discounts on technical publications, discounted consulting services, free listing in the Cement and Concrete SA directory, what used to be called the old Concrete Society source book. That will be live very soon. And then your hyperlink logo in Concrete Baton and on the website. These are, to name a few of the more tangible benefits, but as we all know, being part of a professional body actually gives you many other benefits. So welcome to those who've already taken up membership. Just brief membership category overview, but this can all be seen on our website with the fees. Please familiarize yourself with these and see where you can fit into the body of Cement and Concrete. On the 13th and 14th of July, we're going to be hosting YCRETS, the Young Concrete Researchers, Engineers and Technologists Symposium. This is a virtual symposium, and coupled with that, we've just launched the Young Concrete Researcher Award. Please go to the website, the Cement and Concrete SA website, /YCRETS, look at the nomination form for the Young Concrete Researcher Award, and please nominate those researchers that you want to be recognized. As I mentioned in the previous CONCRETEfix, our branches are now operational. You'll be seeing more activity from the branches. In KwaZulu-Natal, Kevin Volmink is the chair. In the Inland branch, it is Janus Bester. In the Western Cape, it's Villiers Blom. And in the Eastern Cape, Patrick Flanagan. So welcome to all the branch chairs, and keep your eyes open for the new branch activities that will take place, or that will start taking place quite soon. Then, very exciting news, the new edition of Fulton's Concrete Technology, that is the 10th edition, will be launched very soon. Keep your eyes open for the information about the launch edition, and This promises to be a highly updated and expanded edition from the previous 9th edition. So please stay tuned to see more about Fulton's concrete technology. Remember that the School of Concrete Technology still runs its online courses. Look at the program, and please, if you remember, make use of your membership discount to attend some of these courses. The Information Center that you've all come to know gives free access to all Cement and Concrete SA members, and then the books that are for sale can either be bought directly from the Information Center. If you remember, make sure that you contact the Information Center to get your membership discount, or you can visit Bid or Buy, where you can buy the books online. So, Cement and Concrete SA, we're building a future together, and we hope to welcome everybody as members of the body one of these days. I'm stopping the share now, because actually what I would really like to do is to introduce you to Professor Hans Boyshausen. He's the person that's going to be talking to us today. And just shortly, Hans Boyshausen is Professor for Structural and Materials Engineering at the University of Cape Town. After completing his first degree in structural engineering in Hamburg, Germany, he obtained his MSc and PhD from UCT, and he subsequently made South Africa his home. His research interests concern advanced concrete technology, assessment and repair of concrete structures, durability design and service life modeling, recycled aggregate concrete, and concrete with low clinker contents for improved sustainability. He manages the concrete laboratory at UCT and acts as industry consultant on all aspects related to concrete technology and associated forensic engineering. So Hans, it is over to you. Please share your screen with us, and we look forward to what you're going to present. Thank you so much.
Hanli, thank you very much for that kind introduction, and also for the invitation to come and present. And Hanli, we met in 1999. Not sure you can remember, when I was a master's student and I came to the library, and you guys helped me out with coffee and books and literature and all that. So yeah, we go back a long way.
Hans, I remember that. And you see, even in those days, we saw potential. That is why we made sure that we bought you a cup of coffee.
Okay, cool. Thank you. Okay, thank you everyone for coming to attend this talk. So you can see my title there, Design for Concrete Durability, International Trends in South African Perspective. I gave Hanli this title about 4 weeks ago, because I had to give her some title, and then I tried to make sense of that title and build a presentation around it. So let's, I hope it's interesting for you. What you can see on the picture, of course, that is UCT. And, oh, hang on. This doesn't work now. No, okay, sorry, I must do it like this. Okay, talking about concrete durability, there would be many different things we could be talking about. For example, alkali silica reaction, as you can see here very nicely in Cape Town in the harbor, in front of the stadium on these dollars. We could be talking about acid attack, one of the main issues we have with our infrastructure also in the future, for sewer pipes, for example. We could be talking about shrinkage, cracking in floors or facades and the problems. We could be talking about construction defects and durability issues, but we are going to focus today on reinforcement corrosion, because that is probably the field in which most of the service life design models, durability prediction models, and design philosophies are being developed and applied worldwide. And one reason why we do so much research on durability of reinforced concrete structures with regards to reinforcement corrosion at UCT is because Cape Town is located along the ocean, as is Durban and many other parts of the South African infrastructure. And if you look at our infrastructure along the ocean, there are many things you can see. For example, if I take my boys, that's a bit of an older picture, on a boat ride in Cape Town Harbor, they look out for the pirate ships, for the wildlife. We are always hoping to see some of this, whereas all of that doesn't interest me at all. What I look at is this, and I'm not referring to the mountain. I'm referring to all the damage you can see there on the seawall. That's a close-up Because whenever you're close to the ocean, and it doesn't have to be that close even, you see damage, reinforcement, corrosion, cracking, delamination, spalling, rust stains all over. And being an engineer working in the field, that always makes me very happy. Another picture here, that is the silo hotel. I took this picture before this was renovated, when it was still only the silos. Much to my dismay, this now looks much better, and you don't see any damage on the surface any longer. But just walking along our infrastructure in coastal cities highlights the urgency with which we not only have to repair and maintain existing infrastructure, but also the urgency with which we have to develop solutions to design a durable infrastructure for future construction. So the content of my presentation is I'll give a very brief review of prescriptive approaches for concrete durability design, talk about performance-based design, principles, test methods, also compare what we do to what is being done overseas, talk about current trends, talk about application of these approaches. There will be changes in exposure classes to be expected in the standards, which I will introduce to you, and put this on the background on some of the challenges we are facing in research and application of durability design methods. And I'll try and tell you after that, what now? What do we actually want to achieve and how can we do it? Design approaches for durability of reinforced concrete structures. So we have prescriptive and performance-based approaches. The prescriptive approach works on a prescribed concrete mix composition in terms of water cement ratio, cement content, and cement type. Performance-based approaches, on the other hand, work on defining test values, so performance-based values that link to the actual performance that is expected of a particular concrete. And looking at these prescriptive requirements that we find in the Eurocode, which are also very similar to what we find in the current South African standards, you can see that for a certain exposure condition, this code gives limiting values for a maximum water cement ratio, minimum concrete strength, and minimum cement content. And essentially what this means is that the code assumes, or the designer is given the directive, that as long as these mixed design parameters are met, the concrete will be durable in this particular environment. And the problems with that approach are that there is a weak link between water cement ratio, cement content, and strength with durability. And also this doesn't allow to exercise innovative or economic concrete mix design, because you always have to adhere to these guidelines, no matter if you find other ways to make the concrete durable. And also for the client and the engineer, you cannot account for construction quality and on-site conditions using a prescriptive approach. Can I just point out that some of you are not unmuted, and I hear lots of background noise. Can you please mute your microphone? Thank you. And the last problem with the prescriptive approach is that we cannot verify the as-built quality of the structure. So while this approach has been used for many years to some degree of success, there are many shortcomings which can be addressed with using a performance-based approach. You can see here the definition of a performance-based approach as given by the American Concrete Institute. Essentially, a performance specification defines required test results, which you can measure with a test method, which then form the criteria to judge the performance and verification methods. And now it comes without requirements for how the results are to be obtained. So essentially, this philosophy says that no matter what you put into the concrete or how you produce it, it is acceptable as long as you verify with a suitable test method that it in fact meets relevant durability criteria. And performance-based approaches are of course not new. If you look at, for example, when we talk about fresh concrete properties and the workability of concrete, what we are concerned about is how well can the concrete be transported, placed, or pumped, How well does it flow around the reinforcement in the formwork? How well can you strike off the surface to give it a certain appearance, and so on. And all of that relates to the workability of the concrete. And we define workability using the slump test, which of course the slump test has got nothing to do with any of those things that I just described. But we have accepted that there is a certain correlation which allows us to use the slump test as a simple indication of what we would expect in terms of workability, even though the test method as such doesn't really reflect on what we're actually wanting to identify. And the same is true for compressive strength. So we want to model the structural performance of a concrete structure, for which we need the compressive strength, that is the behavior of the concrete under ultimate stress, which could be very different for a beam or a column or a slab and so on. And how we characterize the concrete for doing so is we cast a cube specimen, we put it in water for 28 days, and then we put it between two steel plates that move towards each other to crush the concrete. It's actually a tensile test because the concrete fails in tension, but we call this the compressive strength of concrete. And we use that in the design. And of course, once again, there's a very weak correlation between what we actually measure on the cube and what we have in the structure in terms of stress and strain scenarios and how the concrete would fail in the actual structure. But it's a very useful performance test that we have come to accept. And now the same principles can apply when we talk about durability design. In this case, to compare this to the concrete cube test that we use in structural design, in this case, we talk about service life design or durability design. And in our particular case today, reinforcement corrosion. And the most relevant factors that cause reinforcement corrosion worldwide and also in South Africa are carbonation and chloride ingress. So we now define test values that characterize how the concrete is resistant against carbonation or chloride ingress in the same way as we use the cube test to define how the concrete might behave in the structure under loading. Once we have defined those test values and once we have test methods, we can specify limiting values for durability for certain exposure conditions. And we can use this approach only in the design stage to identify suitable concrete mixes for a certain environmental exposure and service life, or we can use it also for quality control and conformity assessment to essentially verify that the concrete structure as built meets the design requirements. So as such, those test methods give us a very good tool to design and test concrete structures to make sure that they are actually durable for the intended service life duration and the intended exposure condition. And looking at the exposure conditions that we use to define the environmental exposure, they are basically different ways how to apply those in the design. So we can have standard exposure classes in combination with prescriptive design, so those that we pick from a table. We can also have standard exposure classes in combination with performance-based design, which, for example, is something that we do in South Africa. We have certain defined exposure classes that we use for our durability index approach, which is a performance-based approach. So we use standard exposure classes in combination with performance-based design approaches. In a more sophisticated design environments, engineers can quantify the environmental load, taking into account the prevailing site conditions, carbon dioxide concentrations, chloride concentrations, temperatures, and so on, which is typically done in combination with performance-based design. And lastly, quantification of the environmental load can also be done in combination with service life modeling, performance-based design, limit state design, and full probabilistic approaches. So we have 4 different levels of complexity here, each of which are based on defining the environmental exposure that the concrete structure is subjected to. And most of us are used to the existing exposure classes, especially those working along the coastlines or in Durban, PE, Cape Town, Our main concern is the durability of concrete structures in marine environments exposed to chlorides. And in this field, there has been a development recently because the FRB Model Code 2020, I put 2020 there in inverted commas, because it will possibly be published only 2025, but it will be the basis for how we design concrete structures in future. The FRB Model Code is also the basis of the Eurocode, which in turn is the basis how we will design our concrete structures in South Africa in future. And in the Model Code 2020, there has been an updated on exposure classes, which you can see here summarized in this figure. You can see when we talk about marine exposure classes, we have different exposure zones. On top there, you see the sun shining, and just below there, you can see airborne zone of exposure, XS1 and XS3A. I'll explain what that means in a minute. And then we have parts of the structure that may be exposed to splash and spray action from the water. Then we have the tidal zone, and we have the submerged zone. And each of these exposure zones comes with a different degree of aggressiveness, and therefore might require different design considerations with regards to mixed constituents, mixed design, curing, construction, detailing, and so on. And now, what has really changed? So this will be the new environmental exposure zones included in the model code, and therefore in the future of also most of the other codes. What have changed is that in the past, or in the existing codes, we do not assume that airborne chloride exposure is aggressive. It has always been falling into class XS1, which is the least aggressive exposure zone for marine structures. In the new codes, there is a statement that you can only assume structures to be in exposure zone XS1 if you can prove that there is a low risk of chloride ingress. And that is quite an important change, because we no longer automatically assume that anything that doesn't have direct contact with seawater is actually no concern for durability. And in the same line, airborne exposure has now been put into the most aggressive exposure class, XS3, where it is defined that the aggressiveness of airborne marine chloride exposure depends strongly on the prevailing environmental and geographical conditions. So elevation, wind, fog, distance from the sea, and all of that. So we can no longer just assume that airborne exposure is fine. We have to define whether it is actually a risk or whether it's not a risk. And looking, for example, at the problems we have in South Africa. I'm standing here on a roof in Durban, overlooking the harbor. I did a condition assessment of a structure. Looking back at the structure, this is what I was looking at. You can see clearly this part of the structure is not in the splash spray zone or tidal zone. It's all airborne chloride exposure, which has led to severe deterioration of the structure. The same we can see in Cape Town. This is a structure in Cape Town, which is also not exposed to direct seawater, but you can see airborne chloride exposure. And on that side was quite interesting to see that they are warning. So there are these safety warnings, but what they should actually be concerned about is pieces of concrete falling on the head. It's a risk that is often underestimated. But the point I'm making here is that airborne exposure can be quite severe. And we will in future have to change our design thinking and think closely about where is my structure in correlation to the wind direction and elevation, to make sure we can prevent structures looking from we can prevent structures from looking like this in the future. So, and the new codes will also make the recommendation in order to make design easy to possibly use the same concrete mixes or the same design assumptions, also cover depth for concrete structures falling into exposure classes XS1 or XS2, meaning airborne exposure that is not of concern, and permanently submerged structures, which typically don't see much corrosion because there's an absence of oxygen that can reach the steel to facilitate corrosion. And personally, I believe that we should consider airborne exposure, if it is aggressive, to be as aggressive as tidal and splash zone exposure, to make design simple and say, okay, either we have aggressive environments or we don't have it. It doesn't make much sense from a design point of view to really subdivide aggressive exposure further, especially in a conservative design environment. Okay, looking again at this slide here, in this case pointing out the design for durability methods that can be followed by the engineer. So the most simple one is the prescriptive design, but as I pointed out, that actually doesn't work very well. Then performance-based design in the simple way that we typically do it in South Africa, at least in the application stage. Then performance-based design in combination with partial safety factors. That is done, for example, by the universities or by agencies such as SANRAL when they define limiting values that can be used in the more simple way of performance-based design with standard exposure classes. And lastly, the method that is done mostly overseas in Europe, for example, for large monumental structures, bridges, like large bridges, tall buildings, and so on, service life modeling, performance-based design, and full probabilistic approaches. There is another method for durability design, and that is called avoidance of deterioration. So, and that essentially includes using materials that will not deteriorate. So stainless steel, you can use coatings on concrete that prevent ingress. And often engineers don't like to use this because this method is perceived as being expensive and often not necessary. Engineers tend to shy away from telling the client that they should use stainless steel or a coating and would rather try and make the concrete more durable. And also, if you look at researchers, hardly anyone is doing any research on this because this is just perceived to be not interesting or too simple. So in the community of engineers and researchers, this is somehow being the little annoying sister of proper durability design. And when I talk about annoying sisters, you can see as a more recent picture of my kids. You can see how annoying she looks, and you can see how my boys are not impressed with her. And I had to think about this when I try to give this avoidance of deterioration approach a name. I think it is like an annoying little sister that no one actually takes serious. And I will come back to that point later. Now back to how we do things in South Africa. So the durability index approach, the procedure. The engineer selects a design environment and the expected service life duration. Once we have that, we design or we select concrete mixes to conform to design specifications for durability indexes, OPI, chloride conductivity, water sorptivity. Then before production or construction, those mixes are tested for compliance to see whether they are fit for purpose. And then during or after production, we test the actual structure for compliance to see whether it conforms to the specified values. That is the very simple structure of the performance-based approach that we use in South Africa. And most of you might be aware of this simple example. So SANRAL has implemented this, and that's an extract of the design requirements for national infrastructure, bridges, culverts, and so on, for a service life of 100 years. You get for the different environmental exposure classes and cover depth, certain limiting values for the oxygen permeability index test are specified. Looking at what's happening worldwide, so what has been implemented in South Africa, thanks to Edwin Mosley, who I saw is in this meeting. Hello, Edwin. Thank you very much again for supporting this approach, which really is cutting edge, because South Africa is still the only country worldwide using performance-based approaches on a large scale, and has done so for about a decade. Whereas most of the other countries, or actually all of them worldwide, are still stuck in trying to develop suitable test methods, calibrating test methods with service life models, developing limit state design models to then define limiting values for the test methods that they are using. But it is certainly a huge trend worldwide that all the major regions, and that is North America, South America, Europe, Asia, Australia, they're trying to develop their own performance-based approaches. And at the moment also, the main national guidelines are being updated, including the Eurocode and the FRB model code. And all of these contain much more information and much more guidance on using performance-based approaches for durability than what you would have found before in the codes. So certainly we are on the right track in South Africa with our durability index approach. Looking at test methods, so there are different test methods that are available throughout the world. We have been involved in some research where we compared different test methods for durability characterization of concrete. Here we spent some time at a laboratory in the Netherlands and compared different test methods from around the world, from Europe, from North America, from South America, and from Asia. And we had all these different experts coming together to try out their test method on these precast concrete elements to see how those test methods compare to each other. So what you see in this picture, that is a Japanese method which measures oxygen or like air permeability on concrete, where a silicone is applied to the surface with a little, with the center being remaining without silicone. And on the little center portion, as you can see in the left, then the oxygen permeability is measured, whereas the neighboring concrete surfaces are sealed off. And then you can just remove the silicone after measurement. Those measurements that are taken in situ normally rely on using moisture measurements of the concrete as a calibration for what you have measured. We don't do that in South Africa because we take samples from the structure and test it under specified conditions in the laboratory, controlled conditions. So we don't have to take account of the moisture content, which is one of the problems of most of the in situ based methods, that you always have to interpret your penetrability test methods with the prevailing moisture condition in the concrete. So if you measure these values in different seasons, you would measure different values. So you have to interpret the concrete quality accordingly. Here you see resistivity being measured. We have a similar test. We measure chloride conductivity, again on lab-based samples. Resistivity is the inverse of conductivity, and this test method is largely used in Spain and South America to predict chloride ingress. Here you see a method from Northern Ireland, where you basically, in a localized spot on the surface, expose the concrete to an actual chloride solution to then measure how much of that chloride solution enters the concrete to determine the chloride ingress resistance of the concrete. And lastly, this is the torrent test, which measures the permeability of the concrete in situ. A very useful test, similar to the other Japanese test method I showed you, but much more practical. And we also have worked with this test method a lot in our laboratory. And that probably is the leading test method worldwide applied for designing concrete structures for carbonation and chloride ingress, the torrent tester that you can use in situ. We have compared the torrent tester to our local oxygen permeability index test. They both work on very similar principles in terms of measuring the permeability of concrete under a pressure gradient. And we compared the South African design approaches to the Swiss design approaches where this method is being used. And for example, one way to do this is to characterize the concrete. And in our case, we say we have very high permeability, moderate, and low permeability. And in Switzerland, they talk about poor concrete quality, good, very good, and excellent concrete quality. And we tested dozens of concrete mixes to find out that in nearly all cases, we would place the concrete in the same category of quality, which of course confirms that both these methods have similar merits in identifying the quality of the concrete, which is quite encouraging. And at the moment, we are trying to identify how we can in South Africa maybe use a combination of the torrent tester and the OPI test to make use of the advantages of both methods, and more on that in future research. Now, one of the outcomes of all this testing that we have done there on those precast elements with all these methods, we used the test results to rank the concretes in terms of quality. What you see here is different methods used to design concrete for exposure class XC, which is carbonation-induced reinforcement corrosion. And what is nice to see here, that in principle, with a bit of scatter, all these methods can agree on the principal quality of the concrete. So I would take this as a positive sign to say, worldwide, the developments have led to test methods that give us a similar picture of the quality of the concrete. So this confirms that we can use these test methods in the design and quality control of our structures. Looking at exposure conditions related to chloride ingress, we had a very similar picture where on average, the test methods tended to agree. So once again, I would say thumbs up, we are on the right track. However, then we also compared the service life prediction. Now we use the test values obtained to predict or to quantify the service life of our concrete structures. And there we have totally different values for the different concretes. So, and for example, for A concrete, looking at the first one, the values would range between 25 years to more than 100 years. So there was no consensus at all. So all these methods, while they are quite useful in rating the concrete in terms of quality, and therefore whether a concrete is more fit for purpose for a certain application than another concrete, they failed in giving a reliable quantification of the actual service life, which tells us that all these complicated methods of designing for durability and probabilistic approaches and all that might be actually quite vague. So I think there's a bit of a warning here as to how we should use all these methods. Then, in order to investigate this further, I'm going to give a brief review here on some test results on chloride ingress that we have obtained along different structures along the coastlines of Southern Africa. And you can see here, summarized in the various graphs, always we took different core samples from a particular structure from similar elements. And you can see how the test results differ, and even though they were taken on the same structure. Some more examples here. So what we can see from this is we got a very high variability of test results, even when different samples are tested from the same or neighboring elements. And based on the observed scatter, reliable chloride prediction is very difficult, if not impossible to achieve, which once again speaks to the point that it is actually quite difficult to model durability in a way that gives us a quantification of the service life, which points out that all these more complicated methods to design for durability might be slightly, let's say, inaccurate. So when we use our service life models and we use diffusion models to model chloride ingress, the question is, how applicable are these really in the field? Another issue is that when we test concrete for its penetrability properties, we always do that on uncracked concrete. Here you can see some research done by Mike Oceno, who is also there. Hello, Mike, who's now in WITS, where we investigated the influence of crack width on the corrosion of concrete in the marine environments. And on the graph on the left, we are comparing corrosion rates of uncracked concrete to corrosion rates in concrete that has got a hairline crack. And you can see that even if the concrete has got a hairline crack, that means you can't even measure the width, corrosion rates are much higher compared to uncracked concrete. On the bottom right, we are comparing hairline cracks to cracks of 0.4 millimeters crack width. So what these graphs are showing is that even though we measure penetrability on concrete on uncracked samples and use that in our service life models, we In situ, we can possibly very often expect much higher corrosion rates because our concrete very often is cracked from shrinkage or structural cracks and so on, which once again talks to our approaches that we use for service life modeling not being very reliable or relevant. So, and I'm not sure if you're familiar with this type of curve. It's the Gartner's hype cycle. And often many of our research projects or many of our developments work like that. You come up with an innovation trigger. And then you've got very high expectations as what you can achieve with your work. And then you come to the peak of inflated expectations, followed by this trough of disillusionment. And then slowly, if you're lucky, there's a slope of enlightenment and a plateau of productivity. When I look at this curve, it reminds me as what most of our students go through. So looking at our students, and you can see here a couple of them who have finished their PhD or masters with us in recent years. Normally after about, let's say, 2 or 3 or 4 weeks, they are right up there and they are full of motivation and they think they can change the world and they have it all figured out with their research. And as they go into the literature, they find out how complicated it is to see how little influence their work might have to the overall picture, and they fall into this stage. And if they take 2 years to do their masters, they maybe hover around here for about 16, 17 months, and slowly we help them out of that through good supervision, so that at the end of their masters, they come up with something that is actually quite useful and forms one of the puzzle pieces we need to actually make a good difference to our engineering society. Look, and applying the same principle to durability design and looking at my own experience here. So this is now my Gartner's hype cycle from the last 20 years. Starting with the problem of deterioration of our infrastructure and how urgent it is, followed by all the nice developments that we've made in test methods and durability design and service life modeling, chloride ingress modeling, our test methods comparing to overseas test methods. That's all absolutely awesome and points in the right direction. If I then think about the limitations in terms of accuracy and cracked concrete versus uncracked concrete, and I wonder whether we're actually not maybe trying to be too positive. But looking how we can get back up again in terms of making sense of all this, I think how we need to apply our knowledge and our research here. We need to know the limitations of our durability design approaches. And we need to use the approaches that we have in a sensible fashion to make sure our concrete structures are more durable than what they would be otherwise. So we accept the limitations. And because overall our aim is to improve the durability of our structures. And I believe with this performance-based design, even though it has limitations, we certainly can much better design structures for durability compared to the traditional prescriptive approaches. And also, of course, these test methods allow us to do proper design specifications and quality control and conformity assessment. So I do believe that we are on the right track, even though these approaches might not give us as much as we had hoped maybe 10 years ago. And that is my personal assessment of what is being done worldwide in terms of durability design. And then coming back to the actual aim, the underlying aim of all of this, service life modeling, durability design, exposure classes, all of those are just objectives or methodologies to the aim of providing more durable concrete infrastructure. And I think there's a simple solution. And coming back to this little annoying sister that I said earlier, looking at the avoidance of deterioration approaches. So we have recently done quite a bit of research on using hydrophobic coatings on concrete to increase the service life. And this is a paper that you can expect to come out sometime soon in Concrete Beton. I think it's the next issue, which was co-authored here between myself and Harris Sohawan, a previous master's student at UCT. So what we did here is we wanted to find out how we can use those hydrophobic impregnations to produce durable concrete structures and determine how much the design cover can be reduced through the use of hydrophobic impregnation, to give engineers a quantification method to actually determine what is the effect of using this approach, avoidance of deterioration. So we evaluated the effectiveness of hydrophobic impregnation in poor concrete and also cracked concrete to see how we can extend the service life of our structures. We used a CECA product. This research was sponsored by CECA, and measured bulk diffusion, meaning we put concrete samples, treated and untreated, and different types of concrete samples in a chloride bath and measured chloride ingress with time. These are the test results. So here you can see chloride ingress into a SAM1 concrete, OPC concrete. The black curve is the untreated sample, and the gray curve is the treated sample. And clearly you can see we have got much lower chloride ingress into the concrete that has been treated. This effect was much more pronounced in fly ash concretes and also concretes containing Corex slag. So what we could see here is that these hydrophobic coatings are very effective in limiting the ingress of water. And if water is kept out of the concrete, you can also keep out chlorides. If you keep out the chlorides and the water, you will not get reinforcement corrosion. So we then analyzed these curves for diffusion coefficients and chloride surface concentrations and so on, to do some service life modeling. And this is the outcome of the service life modeling, where we can compare the required cover depth versus the time of corrosion for the different concrete types that we have measured. For example, looking at a fly ash concrete, assuming we have 100 years of service life that we want to design for, then for a fly ash concrete in this particular case with a water binder ratio of 0.45, we would need about 50 millimeters cover depth to achieve a service life of 100 years in the tidal splash zone. If we look at the values that we calculated for the treated concretes, we only need a cover depth of 10 millimeters. Now, I'm not advocating that we should build concrete structures with 10 millimeters cover, but I think what this shows is that instead of using 50 mil cover, we could possibly get away with 30 mil cover or even 25. Or we can look at concrete structures that have been constructed with too low cover or too low concrete quality and use hydrophobic coatings as a treatment to still achieve durability in our structures. Personally, I believe that if we were to coat or if we were to apply hydrophobic sealants on all our concrete structures in future, we would never again have to deal with condition assessment, concrete repair, and so on, at least not on these newly built structures. So we would never see situations like this on our newly built structures. And applying these surface coatings or these hydrophobic sealants would allow us to produce durable structures at very low cost. It doesn't change the appearance of the structure. And you don't have to do all this design around it. You can just follow this very simple design approach, providing durability by avoiding deterioration. And this speech has not been sponsored by CECA, even though it should have been. But I really strongly believe that as engineers, we should look back at aiming at providing durable structures. And this is a very simple way to do it. So in conclusion, performance-based design approaches are being developed worldwide. South Africa is still at least a decade ahead, even after a decade of applying these approaches, because the rest of the world is still trying to grapple with the approaches and trying to implement them in practice. We will see an update on exposure classes as discussed. We will have to accept the challenges and limitations of our design approaches. But also there, of course, these approaches, even though they have these limitations, have these advantages and opportunities to provide design solutions, conformity assessment, and so on. And yeah, protection against deterioration, as I said, to my mind, is possibly one of the most effective ways how we can in future make sure that our concrete structures are durable for the intended service life. And that's all I have for you. Thank you very much.
Thank you, Hans. I really enjoyed that presentation, and I'm sure everybody that stayed online would agree with me. Are there any questions for Hans? If you've got a question, just unmute your sound, and please, you're welcome to ask the question. We've actually got on the chat, Hans, we've got a question from Dane McGillivray that says, do you have any opinions on the use of colloidal silica as a post-applied measure to improve concrete durability?
If I was in a courtroom, I would now call my Fifth Amendment rights. Look, what I would say, yeah, I mean, it sounds like a very promising technology, but I would like to see test results that actually confirm and support the claims that are being made in those marketing brochures. So it sounds great, but I think we need to still wait and see the evidence.
Thank you. Any other questions for Hans? Hans, I don't see any raised hands. I don't see any questions on chat. So I think what remains for me to say is thank you so much for being willing to share with us, for giving us a very practical insight into a very complex subject, and for making us see the positivity, knowing that, as you've pointed out in your conclusion slide, that we are still ahead in concrete durability testing. So thank you so much. We really appreciate you sharing with us today. Ladies and gentlemen, as Hans pointed out, look out in the June issue of Concrete Baton, which will become available on the Cement and Concrete SA website within the next couple of weeks. Look out for that paper that Hans co-authored. And then thank you again, everybody, for attending. We look forward to seeing you at our next CONCRETEfiX event. You will be notified about that on mailers and in the social media. Hans, thank you for sharing. Everybody, go well, and please stay safe, observe all COVID protocols, and keep well. Take care. Goodbye.